Hello class, this is Mr. Lehman. I want to talk to you today about the ideal gas law, another formula in this unit. So the ideal gas law is pretty cool because we got some new variables here. We have R, which is just a constant. We'll talk about that next. But N is cool because N allows us to figure out the number of moles of gas. And so if we know the pressure of a gas in ATMs, we know the volume of our gas sample in liters, and we know the Kelvin temperature of our gas, we can solve for how many moles of gas. So if you have a balloon, you know the pressure, volume, and temperature. You can figure out how many moles of gas are inside that balloon. R is just a constant. So R is always going to be equal to 0.0821. And so when a gas behaves ideally, as we talked about in the kinetic molecular theory of gases, when we looked at the Boltzmann 3D simulation, if we solve for R, we rearrange R is equal to PV divided by N times T. That if you have the pressure in ATMs, the volume in liters, the number of moles, the temperature in Kelvin, this ratio will always be equal to 0.0821. And there's some units that go along with that. I'm not going to write out the units. 0.0821 is what that is equal to. So let's go ahead and see how we can use this. So let's say we got a balloon. And inside our balloon we have helium. Alright, the balloon is at, let's say, 180 torr of pressure. And let's say the balloon is at 400 Kelvin. And let's say the balloon is 12 liters in size. If we know the pressure, we know the temperature, we know the volume, we can figure out how many moles and thus how many grams of helium gas are inside that balloon. So we have PV is equal to nRT. Pressure is 180 torr. We need ATMs of pressure. So if you remember, how many torr of pressure is equal to 1 ATM? 760, just like millimeters of mercury. So the short way to represent this is 180 torr divided by how many torr are equal to an ATM? 760, or you could do 180 torr over 1 times 1 ATM over 760, which is essentially the same as this. So I'm just abbreviating it so you can see how we put that into our calculator. 12 liters is the volume. It's in liters. I don't have to worry about changing that. We're solving for N. R is 0.0821. Almost running out of room here. Kelvin, temperature 400. So let's simplify what we can. So 180 over 760, that gives us 0.23684211053 ATMs of pressure. We're going to times that by 12 liters. And that gives us about 2.84 on the left side is equal to 0.0821 times 400, which is 32.84 times N. Divide both sides by 32.84. So 2.84 divided by 32.84. Get about 0.086 moles of helium gas inside that balloon. If you want to know how much it would weigh, we're going to take the number of moles and we'll times it by how much a mole weighs. 4 grams of helium is equal to 1 mole of helium. So 0.086 times 4. We get 0.344 grams. Keeping sig figs, we just round that to 0.34 grams. You know, our scales don't have the ability to go out past 2 decimal places, past the hundredths of a gram. Alright, so that's the ideal gas law. Alright, so sometimes you might know the number of moles and be asked to solve for something else, but that's how we use that equation. So if you need more help, come see me. Have a great day.